Alright, welcome back. So now I'm going to go into graphing part 2. So in the first video I sent you, we had, kind of going over our slope. We were going over, various ideas that, what our independent and dependent variables are and how they're reflected on an axis or on a graph. But we also have trends. For example, if we have, say we have a graph, excuse me, that wasn't a great line. So say we have a graph that looks like this. We have one graph where our x and our t, kind of just curves upward like that. Then we have another one. Actually, I'll do this in a different color so it stands out. We have, say, another one where we have our velocity over time. So if something has a graph like this, so if we have a displacement graph like that, we're going to have a velocity graph that looks like this. Our velocity will be linear. Then we'll have an acceleration graph that looks like this. Now you're probably saying, Mr. Mantilla, what the heck is that? That makes no sense. I understand. Give me a minute. So this x is increasing like this because, for example, if you were to drop an object, like I'll do some quick math and it'll make some sense. We have our kinematics. So we have our kinematic equations which we can use when acceleration is constant. When is acceleration constant? If I drop something, like I drop this marker. If I drop this marker, it has an initial velocity of 0. So I can then use this equation. So I'm going to use simple values. We're going to say that Mr. Mantilla, we're going to pretend for a minute that gravity is equal to 2. It'll make the numbers really nice. So we're going to say that our acceleration in our, actually, you know what? I'm going to ask you to remember this and write this down for right now. Like, write down these graphing trends. And I'm going to give you some numbers to work with. And these numbers should actually, then you can punch them into Excel or into a graphing software. And it should be able to, come out nicely. Or maybe I'll just show you on my computer. I don't know what I'm going to do yet. But I will teach you this material. In any case, we know that we can get displacement using our kinematics. So we can use our kinematics to solve for these variables. We can solve our kinematics for velocity final, velocity initial, acceleration, time, and displacement. And I'll also put displacement in y, because as you remember from graphing and coordinate planes, we know that we have our y, our minus y, our x, our minus x. That should look familiar. So obviously we have to consider displacement in y separate from our displacement in our x. Meaning, if something moves up, it has nothing to do with something moving away. Alright, so now we're going to get back to my original thought, where we're going to pretend, we're going to show how these graphing trends work. We're going to show how, I'll put it down here. I'll put small little graphs, little baby graphs. So if a over t is constant, v over t is linear, x over t, or I could do a better slope upward than that. X would look like this. So I'm going to show you how that works. Now, we're going to pretend that gravity is 2, like I said. So we're going to make our A, and we're looking at things only in the y direction right now to keep this simple. We're not pretending that I'm throwing this object anywhere, we're pretending I'm just dropping it. So our A sub y, we're going to say, is -2 meters per second squared. I think that's a fair acceleration to use for this. We're going to say our velocity initial in our y. So VIY is velocity initial in the y. We're going to say that's 0 meters per second. Then we can then have our time, which we don't know. We don't know our time yet. And we're just gonna make time what we want to be. We're gonna make time, we'll say values 1 through 10. So 1 second through 10 seconds. We won't know our velocity final, but we will be able to calculate it. And we won't know our displacement, but we'll be able to calculate it. And I promise you'll see where this is coming from, where I'm going with this. So once I let this go, I want you to imagine for a second now, if I let this marker drop, this marker is going to continuously fall until it hits the floor, or until another force acts on it. So when something goes into free fall, meaning it's in the air, the only force acting upon it is gravity, and it will accelerate towards the ground. Now in this imaginary situation, I want you to imagine that I'm standing on a bottomless floor, and that this marker will be able to fall as long as I would like it to, without having any impeding air resistance, without any other, what I would call contact forces. Okay? So the only force is going to be the field force of gravity. Now, I'm going to just erase the board for a second. Okay. So we have AY, we have VIY, we have T in seconds. Then we're looking for VF, and we're looking for delta Y. Now, I want you to take a second. I'm not going to tell you, but what do you think if this object is heading towards the ground? What sign must delta Y and VFY be? What sign must they be? Okay, they have to be negative. Because we know that the object, if I was to sketch a path of it, if I'm dropping an object towards the ground, it's starting up here at, I'll put delta Y equals 0, and I'll just put delta Y equals negative. It's just going to be negative because it's heading towards the ground. It's heading on our coordinate axis downward. Then we can start doing a few things to kind of clear this up. So we know we have an equation that says delta Y equals VIY times T plus 1/2 AT squared. Now, because I'm dropping this again, we know our VIY is equal to 0. And I can just change my time value to reflect the time. So I can say delta Y then equals 1/2 AT squared for this particular situation. When I'm dropping something and I'm looking for my displacement exclusively my Y, and I dropped it from 0, like if this being omitted, like this omission right here, and I'm going to kind of, this to be omitted needs to have VIY equals 0. Otherwise, you have to calculate it. But if VIY equals 0, then you can just ignore it, because anything multiplied by 0 is 0. And this would be anything dropped out of an airplane, anything kicked in the horizontal direction off a cliff, anything where your Y direction is presumably starting at a 0 velocity, you can make that 0. Okay, so now we have this. So we know our acceleration is going to be -2. So we have delta Y equals 1/2 -2 times, we'll make our time initially 1 squared. So 1/2 times 2 is then -1, and then 1, we'll do PEMDAS actually. 1 squared is 1, and then -2, 1/2 of it is -1, so we'll say delta Y equals -1 meter after 1 second. So we're going to start constructing a little bit of a table. T and x and y. I'll put that in red here. X and y. Then all I have to do is start changing my time value, because my acceleration isn't going to change, gravity doesn't change, unless, of course, I change it to -2 to make my math easy. But we'll say now t equals 2 seconds. So -1 times 4, we have -4. So far we have, when t equals 1, we have x, or I should put y here, y equals -1. T equals 2, y equals -4. T equals 3, y equals -9. And it goes so on and so forth with, like I think you're going to pick up on the pattern. If I make it 4, it's going to be -16. So I hope you can see that. That says t equals 1, 2, 3, and 4. Y equals -1, -4, -9, -16. Alright? So I'm just going to erase this now, because we now have our t and our displacement and our y. And our a continues to remain constantly -2 meters per second squared. Now we're going to see some interesting stuff when we start to look at the velocity. So we have a way of calculating velocity. We can say Vfy equals Viy plus acceleration times time. We can use that equation in our y direction, or I should put